So, um, imagine trying to read a map of a city, right? But before you're actually allowed to look for your street, you are forced to memorize the location of every single brick, every stoplight, and like every pigeon in the entire metropolis.
Right, your brain would just completely crash.
Exactly. I mean, you just wanted to find the nearest coffee shop, but
Yeah.
the system forced you to load the entire universe into your working memory first.
Yeah, it's totally ridiculous when you put it like that.
It is. But today we're looking at how software often does the exact same foolish thing. And, how one developer actually fixed it by completely rethinking how we consume data from the ground up.
Oh, yeah, it's a massive shift in how we handle information.
So welcome to today's deep dive. We are exploring a really brilliant presentation from 2026. It's by a developer who goes by the handle at Lock036, and it's titled Rust Make the SAX JSON Parsing for Yosys Netlists.
Which I know sounds incredibly niche on the
Oh,
surface.
super new.
But the underlying philosophy here, it really applies to anyone dealing with information overload. I mean, we are looking at a radical shift in system design that achieves something called zero-copy EDO.
Okay, zero copy EDA. Let's break that down for everyone listening. EDA stands for Electronic Design Automation.
Right, yeah. It's basically the software used to design microchips.
And zero copy means, well, exactly what it sounds like.
Exactly. Instead of taking data from a hard drive, making this, useless middleman copy of it in your computer's memory, and then translating it into a final format.
Which takes forever and wastes space.
Totally. This method streams the data directly from the disk right into the final data structure. So no intermediate copies, no wasted memory.
It's just straight to the point. But to understand how this developer actually pulled off this zero copy magic, we first need to look at the environment they were working in, which is Yosys.
Right, Yosys.
For those of you who aren't, designing microchips on your weekends, Yosys is a highly specialized open source synthesis framework.
Yeah, it's essentially a translator.
Right. So when hardware engineers write code to describe how a microchip should behave, using a high-level language called Verilog Yosys steps in. It takes that abstract logic and turns it into a concrete, gate-level netlist.
Basically the literal physical blueprint of the circuit.
Exactly. Every single logic gate, every input, every wire connecting them.
And that blueprint gets exported as a standard JSON file, which honestly is where our bottleneck story truly begins.
Because exporting the blueprint is just step one.
Right. For that blueprint to actually be useful, another piece of software has to open that JSON file, read it, and analyze it. And the method you use to read that file, that dictates the performance of your entire software pipeline.
Which is huge. And in this presentation, the developer walked away from the traditional, comfortable method of reading data, the one everyone uses, known as DOM parsing.
Yeah, they totally tossed it out.
And they replaced it with a highly complex SAX parsing method, which resulted in massive speedups.
But before we pit DOM and SAX against each other, we really need to understand the shape of the data they're fighting over. Like, what does a Yosys JSON blueprint actually look like inside?
Well, what's fascinating here is that the JSON isn't just a simple list of parts. It is representing a hypergraph.
A hypergraph. Okay, we should probably define that.
Okay.
Because a standard graph is easy to visualize, right?
Yeah, a standard graph is like a telephone line connecting exactly two houses, point A to point B, just one edge connecting two nodes.
Right, but a hypergraph, if a standard graph is a telephone line, a hypergraph is like a radio broadcast tower.
Well, I like that analogy.
Yeah, a single edge, which we call a hyperedge, can connect any number of nodes simultaneously. So one signal from the tower reaches thousands of different houses at the same exact time.
So in a Yosys netlist, the cells, which are the logic gates, those act as our nodes.
Exactly. And the wires are the hyperedges.
Get it. So a single wire might connect the output of one cell to the inputs of 3 or 4 other cells all at once.
Right. So when you picture this tangled web of radio signals connecting millions of gates, it makes it super obvious why the JSON schema has to be incredibly strict.
It has to be airtight. Looking at the source material, the blueprint is broken down into very specific entities. You've got ports, which are the input and output pins. You've got the cells themselves.
Mm-hmm.
Then you have the connections, which are the arrays that actually map those ports to specific net IDs, the wires.
Right, and you also toss in net names for any wires the engineers actually bother to name, and some optional attributes for metadata.
And that's your entire hypergraph.
Yeah, but hidden inside that rigid structure, there is a massive trap waiting for an unsuspecting parser.
Oh, the mixed type arrays.
Yes. It's a quirk in how Yosys formats its connection arrays. They mix integer values, which represent the actual net IDs, the custom wires we care about, with string constants.
String constants, so like text characters.
Exactly, like the word 0 or the word 1.
Wait, really? So a program is reading down a list, fully expecting a nice sequence of numbers to identify wires, and suddenly it just gets slapped in the face with a piece of text.
Pretty much.
If a parser isn't built to expect that, it's going to crash immediately. Why does Yosys even put strings in there if they aren't wire IDs?
Because those strings represent tied-off signals.
Tied-off signals. Meaning what exactly?
Well, in a physical microchip, sometimes a pin just needs to be permanently connected to ground, which is a 0, or to power, which is a 1.
Oh, I see.
Yeah, it doesn't need a custom wire routed all the way across the chip to connect it to another gate. It's just hardwired to a constant state.
So if you were building a mathematical graph to analyze the complex routing of wires, you really don't care about those tied-off signals.
Not at all. You only care about the integers. The strings literally must be completely ignored.
Okay, so we have a massive complex hypergraph full of these mixed type traps. How we choose to navigate this file brings us to the core battle of this deep dive. DOM versus SAX parsing.
Yes, the main event.
I want to use an analogy here to make the mechanical difference between these two crystal clear for you listening. Let's imagine you're going out for dinner.
Okay, making me hungry, but let's do it.
DOM, which stands for Document Object Model, is like walking into a massive banquet hall and ordering literally every single item on the menu.
Everything.
Everything. And the kitchen rules state that you cannot take a single bite of your food until every single dish is cooked, plated, wheeled out on a fleet of carts, and placed onto your incredibly large table.
Right, and you'd need a table the size of a football field.
Literally. And the table, in this scenario, is your computer's RAM.
Exactly. DOM reads the entire JSON file and builds a massive, complete tree of objects in memory all at once before you were even allowed to analyze a single logic gate.
So the memory it consumes scales perfectly with the size of the file.
Right. It is incredibly easy for the programmer to work with because once the feast is on the table, you can just reach across and grab whatever you want in your leisure. But the memory overhead is just staggering.
Which brings us to SAX, the streaming API for XML, though here we are applying it to JSON.
Right.
SAX is like sitting at a conveyor belt at a sushi restaurant.
Oh, I love this one.
Right. The kitchen is constantly sending small plates down the line in a stream.
Yeah.
As a plate passes by, you look at it. If it's the spicy tuna roll you want, you grab it, eat it, process it.
And if it's an empty string constant plate that you don't need?
You just let it roll right on by into the trash.
Exactly. You never load the whole menu onto your table. You only hold exactly what you were consuming in that exact microsecond.
And the source notes that by switching to this streaming sushi conveyor belt, memory usage just plummets.
Oh, completely drops off.
And interestingly, it is also about 25% faster on average.
Which is huge.
But I have to push back here because this sounds almost too good to be true. If SAX is this faster, leaner, highly efficient conveyor belt that drastically reduces memory and boosts speed, why isn't it the default?
That is the big question.
Right, like why on earth would anyone ever use DOM?
Well, the answer is entirely about the burden of complexity.
There's always a catch.
Always. See, watching a conveyor belt and grabbing what you need, that sounds intuitive for a human brain. We have eyes and context. But for a computer, it requires building a highly complex, incredibly fragile state machine.
Because it doesn't intuitively know what it's looking at.
Exactly. With DOM, the parser does all the heavy lifting, it figures out the structure and hands you a neat, finished tree. But with SAX, the sushi belt doesn't stop to tell you what category of food is coming next.
So you, the programmer, have to write manual instructions to keep track of exactly where you are in the stream at all times.
Right. Because if you lose your place on the conveyor belt,
The whole program crashes.
instantly. Imagine the conveyor belt has opaque boxes inside of other opaque boxes.
Yeah.
Your code has to explicitly say, I just saw an open bracket, which means I am now inside the cells object.
Therefore, the very next thing I see must be a cell name.
And the thing after that must be its properties.
Huh.
You are manually maintaining the context of the stream.
Yeah.
One typo, one unexpected piece of data, and the state machine breaks down.
Okay, let's unpack this because this is where this specific implementation by Lux036 gets wild. To build that precise mechanical handler for the conveyor belt, the developer turned to the Rust programming language.
Yes, specifically a serialization framework called SERD.
And Rust is practically engineered for this exact type of rigorous high-performance task.
Oh, absolutely. And Cerde provides two fundamentally different ways to untack data, which perfectly mirror our restaurant analogy.
Okay, how so?
Well, there's the standard deserialized trait, which is our banquet hall. It's a one-shot command that requires building the whole JSON tree in memory. But then there is a much more obscure trait called deserialized seed.
Ah, the deserialized seed trait. That's the engine of our conveyor belt.
Exactly. It acts as a streaming visitor. It just watches the stream of data fly by and fundamentally requires absolutely no memory allocation for the JSON tree itself.
But earlier you mentioned the burden of complexity. To handle the deeply nested layers of this specific Yosys JSON file, the developer couldn't just write one single seed instruction, right?
No, not at all. They had to create 9 custom seed types.
9.
Yeah, 9. Each level of nesting in the hypergraph requires its own dedicated seed to tell the parser how to handle that specific layer.
So you start with like a top seed for the very outer layer of the file.
Right. And when the top seed sees the word cells roll down the conveyor belt, it physically passes control to a cell seed.
And then when the cell seed finds a specific cell, it passes control to a cell seed and so on, all the way down to the individual wires.
It's turtles all the way down.
If you are listening to this and thinking, wow, that sounds like a miserable, tedious amount of manual coding,
Yeah,
you are absolutely right.
it really is.
It's like a relay race where the baton being passed is the context of what you are reading. The source even mentions that one of these 9 seeds, the Netnum seed, is actually optional.
Right, because some blueprints don't have named wires.
But the developer had to build the seed and incorporate it into the machine anyway, just in case that specific plate rolled down the belt.
You have to be prepared for everything. The event flow through this 9-seed relay race relies on a specific command called nextValueSeed.
Okay, what does that do?
It tells the parser, take this specific seed, advance the stream into the next nested object, process it according to this seed's strict rules, and then return control back up the chain when you hit the end of the object.
So it is a continuous, unbroken path tracing through the JSON file.
Exactly.
And while this incredibly complex 9-seed machine is chugging along, it is actively collecting data on the fly based on some very strict rules.
Yeah, let's look at what they actually kept off the belt.
Okay, so for the cells, they only keep the cell names and an index number. For ports, they keep the names and their bit arrays. For connections and net names, they strictly keep the integer IDs.
Right, they actively throw away those string constants, the tied-off signals, so they never even enter the computer's memory.
Boom, into the trash. And finally, they take all the net IDs, so every single wire connection, and store them in a specific data structure called a B-tree set.
Choosing a B-tree set over a standard list or array is honestly a really elegant piece of architectural design.
Okay, let's break down why. Because if you are just collecting a massive pile of integer IDs for wires, why get fancy with a B-tree? Why not just shove them all into a standard, simple list?
It comes down to what you have to do with the data once you've collected it. When you are assembling a graph, you constantly need to look up unique identifiers.
Right.
And you almost always need those identifiers to be sorted so you can process them deterministically. If you throw millions of numbers into a standard list, you have to spend a massive amount of computational time and memory sorting that list after the fact.
That makes sense. And a B-tree set solves this.
Yes, by providing O of log n insertion time.
Let's translate O of log n for a second. It's basically like finding a word in a dictionary by opening the book to the exact middle, seeing if your word is in the first half or the second half, and repeating that process.
Right, splitting it in half every time.
It is wildly efficient, even when you're dealing with millions of items.
Exactly. Even as the B-tree set grows huge, finding or inserting a number takes almost no time. More importantly, the data is intrinsically sorted as it is inserted.
Ah, so it provides sorted iteration for free.
Free! There is no separate, time-consuming sorting step required at the end. Additionally, this pattern perfectly mirrors the C++ standard set, which makes the logic highly portable for developers working across different systems.
That's a nice bonus. But here's the real kicker regarding the SAX setup. Because of how they handle the stream, there is 0 per element allocation for the connection arrays.
This is the zero copy magic.
We mentioned zero copy earlier, but explain how 0 allocation is actually possible here. If you are storing data, aren't you forced to allocate memory for it?
Well, there is a massive difference between stack memory and heap memory.
Okay, break that down.
Heap memory is like going to the DMV. You have to formally request a block of memory from the operating system, fill out the paperwork, and wait for it to be assigned.
Which takes precious time.
Right. Stack memory, on the other hand, is like the scrap paper already sitting on your desk. Because the scalar values, the simple integers on the conveyor belt, are so small and predictable, they are just stack allocated.
Wow, so the program grabs the raw value off the belt and slides it directly into the B-tree set structure without ever asking the operating system for a new block of heap space.
Exactly. It is incredibly lean.
But, gathering the parts without wasting an inch of table space is only phase one. Phase two is putting them together and proving this complicated 9-seed contraption was actually worth the headache.
Right. Phase 2 is where we build the actual netlist graph.
And mathematically, they are building a bipartite graph represented as G equals V comma E.
Let's translate that out of textbook jargon.
Yeah, please. A bipartite graph essentially means we have two completely distinct camps of entities, right?
Correct. In one camp, we have the physical parts, the logic gates and the ports. In the other camp, we have the wires.
And in a bipartite graph, you cannot connect an entity to another entity in its own camp.
Exactly. You can't connect a wire directly to a wire. It has to go through a port. So the mathematical representation enforces the physical reality of the microchip.
To organize those two camps, the developer used a highly specific contiguous node numbering system. The cells, representing our logic gates, are numbered from 0 up to C minus 1, where C is the total number of cells.
Then the ports pick up right where the cells left off, numbering from C up to C plus P minus 1.
Right. Finally, the nets, the wires, take the final contiguous block, starting at C plus P up to C plus P plus N minus 1.
And creating a perfectly contiguous block of numbers isn't just for neatness.
Right. It allows the software to use simple, lightning-fast arrays for lookups later, rather than slow, cumbersome hash maps.
Exactly. But here is the most crucial part of this entire endeavor.
Get me.
The output of this complex SAX method is identical to the output of the old memory-hungry DOM method.
Identical.
Identical. That is the ultimate correctness guarantee. Yeah, because in electronic design automation, it is not enough to be fast. If you drop a single wire in a microchip blueprint, the entire processor fails.
Right. It's garbage. They have to be perfectly right.
They verified this with a full round-trip test, but they actually went further. They built 6 dedicated SAX test cases specifically to mirror the existing DOM tests.
Oh, wow. Like what?
They tested a simple AND gate. They tested 2 inverters sharing a single net. They verified that the string constants, those tied-off signals, were successfully thrown into the trash.
That's good.
They tested what happens if the optional net name section is completely missing. They tested empty cells that only have ports.
Basically every edge case.
Yeah, they even fed it invalid JSON with missing modules just to make sure the SAX parser threw the exact same error message as the DOM parser.
So it is a true seamless drop-in replacement.
Yes. The subsequent programs in the pipeline have no idea whether you use DOM or SAX to read the file. They just receive the perfect identical blueprint.
Okay, so we know the blueprint is correct. We know it doesn't hog memory. But here's where it gets really interesting. Did all this complex coding actually buy the developer any speed?
Well, the developer ran benchmarks using the Criterion tool in Rust. They ran a release build with 100 samples for each file size using synthetic Yosys JSON files.
Okay, let's dig into the numbers. How much time did they actually save?
So for a small file, which they defined as 100 cells, the DOM banquet hall took 2.11 milliseconds. The SESET's conveyor belt did it in 1.66 milliseconds.
Okay, so that is about 21% faster.
Right, a very solid improvement for a small workload.
Let's jump to a large file, 2,000 cells. DOM took 28.2 milliseconds. SX took 21.4 milliseconds.
That is roughly 24% faster, so it scales beautifully as the blueprint gets massive.
But the sweet spot is the medium file, 500 cells. DOM took 7.60 milliseconds. SX crushed it in 5.32 milliseconds.
Wow.
That is a 30% speed up.
And if we connect this to the bigger picture, that 30% spike perfectly illustrates the hidden tax of DOM parsing.
Like, why does the gap widen at the medium scale, rather than just scaling linearly?
It's all about tree building overhead. When you use DOM, you aren't just reading data. You are forcing the computer to dynamically build a massive interconnected tree of objects and arrays in memory.
Right, all that DMV paperwork.
Exactly. At the medium scale, the proportional time the CPU spends acting as a memory manager, allocating new blocks of heap space for millions of tiny objects, reaches its absolute peak relative to the file size.
So when files get massively large, other bottlenecks like cache misses start to level the playing field slightly. But at the medium scale, The DOM memory management tax is brutal.
It really is, and SX bypasses that tax entirely.
Because by just watching the conveyor belt, SX completely avoids those dynamic object and array allocations.
It eliminates the need to use hash maps just to look up a field name. It stops intermediate string copies from happening.
It just extracts the raw stack allocated data and pushes it directly into plain data structures using a simple push command.
Yes. It is the absolute shortest possible physical path from the raw file on your hard drive to a usable data structure in your processor.
Which is incredible.
Uh-huh.
But this does raise an important question. The source material explicitly addresses a caveat in a section they call the family portrait.
Right, the language comparison.
We've seen SX absolutely dominate in Rust. But does this strategy work perfectly across all coding languages? Like, if you're writing in Python, should you immediately rewrite all your parsers to use SAX?
The short answer is a resounding no.
No, why not?
The developer noted that when they tried this exact same streaming conveyor belt strategy in Python, the results were highly mixed.
Wait, why would a strategy that yields a 30% speed up in Rust fall flat in Python?
It comes down to the mechanical reality of the language environment.
Okay, explain that.
Rust and C++ are compiled languages. They translate directly to machine code, making them incredibly fast at running the tight, repetitive loop required for a complex state machine. Python, on the other hand, is an interpreted language. When Python uses a library called JSON to run SX, it has to constantly evaluate the state machine logic through its own internal event loop.
Oh, I see. So the cost of running the conveyor belt logic in Python, constantly asking, what box am I in now, what comes next,
Yes,
is so high that it outpaces the savings you get from avoiding the DOM banquet hall.
exactly. It's a brilliant reminder that algorithmic efficiency doesn't exist in a vacuum. It is deeply tied to the specific mechanics and limitations of the language you are using.
You can't just copy-paste a philosophy. You have to actually understand the physical reality of the system executing it.
100%.
So what does this all mean for you listening? Let's synthesize this whole journey. Developer at Lux036 didn't just tweak a few settings right. They wrote about 900 lines of custom Rust code.
Yeah, that includes a massive 630-line chunk dedicated purely to the Yosys SAX data struct and those 9 incredibly tedious deserialized seed implementations.
It is a significant, heavy investment of engineering time. But by making that investment, they created a perfect, identical drop-in replacement for the original function. A replacement that cuts memory usage down to the absolute minimum and reliably speeds up the parsing process by 20 to 30% in compiled languages.
And that is why this highly specific case study matters to you, whether you are writing hardware synthesis tools or, just trying to organize a massive data project at work. It perfectly illustrates the ultimate engineering trade-off.
Front-loaded complexity.
Right. You take on the burden initially. You do the incredibly hard, tedious work of building a 9-seed state machine up front.
You map out every possible contingency so the machine never gets lost.
And by doing that grueling work once, you guarantee long-term zero-copy efficiency. You build a system that runs effortlessly forever, catching only what it needs as it flies by.
Instead of forcing the system to carry the weight of the entire world every single time it boots up.
Exactly. But it makes you wonder, though, if one developer can design a complex state machine to effortlessly stream massive hypergraph blueprints without blowing up their computer's memory.
What other bloated DOM-style bottlenecks in our daily digital lives are just waiting for a streaming revolution?
There's got to be plenty of them out there.
Definitely. So next time your system, whether it's your laptop or, hey, even your own mental bandwidth starts bogging down, ask yourself, are you trying to load the entire menu onto the table, or do you just need to find the tuner roll? We'll leave you with that.